this suction pressure enters that compressor, it's cooling the motor at the bottom and picking that heat and moving it up. Now, what's it doing with it? It's going into the condenser. So if you're on a very small scale, if you have an air conditioner at your house, the condenser's outside, that's where we're rejecting the heat. So if you went out and you were mowing your lawn or you're weeding or playing with the kids or whatever, if you're ever out by your air conditioner, that fan that's at the top of your air conditioner, that's blowing up, that's removing heat, and it's sucking the air in from the side of that condenser, which has the heat that we just picked up in our evaporator, our compressor, and it's rejecting that heat outside where we don't want it, okay? Also, on a condenser, it enters typically on a condenser, the refrigerant enters the condenser from the top. Why? Because it's a vapor. As it moves down the condenser, it starts to condense as it rejects the vapor, and it becomes a liquid. And obviously, liquid is heavier than vapor. Now, moving on to the metering device. In this case, it's a TXV, okay? Two things we're doing here. Obviously, we're metering the refrigerant, but we're changing the state by dropping the pressure. So think of it like this. Why do we need a TXV? Why do we need a metering device of any kind? We have to have a pressure drop. And a good visual for that is you go to the gas station or the convenience store, you go to the air pump, you're airing your tire up. Well, if you didn't have that gauge at the end of it to hook up to your tire and it was just a hose and you turn that on, the hose would just keep blowing and that air compressor would just keep running and running and running and never be able to build up pressure. And that's the way I like to look at the TXV. It's actually stopping that pressure drop, pushing back on the compressor, and it's able to balance, keep that pressure up for us to change the state, okay? Now, this is the way I was taught years ago. I stole this off of the internet, but you can find this anywhere. I did this for a fun fact recently, and I got a lot of feedback, positive feedback, so they never heard of it, even from instructors. But 7 years ago, my first vocational school, this is the way my trainer taught us. And what he said was, he made it a sports analogy. I like to do sports analogies. In this case, I'm going to use the baseball sports analogy, okay? And what he said was, Don, when you're out in the system, no matter how large it is, first of all, identify those four components and think of it as a baseball diamond. And he said to me, his name was Jeff, and he said, think of the home plate as a compressor and think of the first base as a condenser. And as you round first base and head for second base, I want you to think of that as a metering device. And when you round third, I want you to think of that as the condenser, and then you're coming on home. But what he was really trying to tell me is not only telling me what's inside that line, high pressure vapor, high pressure liquid, low pressure liquid, and low pressure vapor. What he really was telling me is, hey, on this side of that pitcher's mound, over by the first base, everything over there is high pressure, whether it's liquid or whether it's vapor, it's high pressure. On the other hand, on the other side, whether it's liquid or vapor, it's low pressure. Okay, so that's a nice way for kids or people coming out. I say kids, young men, young women coming out of the vocational schools or maybe on the job training that can get a good visual of what's going on. And you can use any sport for this. I just chose the baseball field. The thing I want to add here that this doesn't have, if you were to draw an imaginary line from third base or the evaporator to first base or the condenser, above that line, above that pitcher's mound, everything would be liquid and everything below it would be vapor, whether it's high pressure or low pressure. So that's a nice way that I try to, this wasn't in our books when I first hired in, and they added it, the baseball diamond theory, after they hired in because they thought it was a great way to teach. So let's talk about refrigerant fundamentals. Refrigerant is a chemical compound which is capable of changing its state from liquid, vapor, and liquid while maintaining a chemical stability. And that's a fancy way of saying all day, every day, in some cases, 365 days a year, we're going from liquid, vapor, back and forth, okay? Now, the reason I want to point that out to you, unlike a car that has motor oil that you need to change the oil every 3,000, 5,000 miles, in a perfect world, which we know it's not, you should never have to touch that refrigerant again. It's not until Don or someone like me comes up and puts long hoses on it or exposes it to air or contaminates it that we have trouble, okay? So that's the thing about refrigerants. They don't just pluck them out of the sky. Really, almost all liquids on the face of the earth are refrigerant. Water is a refrigerant. It actually has a number. It's referred to as R718. and we use it in boilers and chillers and those kind of things. And then last but not least, we need a relatively high latent heat. Now, if you were Google latent, okay, you would see the word hidden. It's hidden heat, okay? And then last but not least, we have a very low boiling temperature. For example, water boils at 212 degrees at atmospheric pressure, okay? But it has to have those two capabilities. And this is a nice little graph. I know it's busy. I know it looks complex, but I'm going to try to do my best to give an analogy here that I use in classroom every time I teach this. And this is for beginners, the first 2-year students type things. So it's first of all, sensible heat. And these are important things to know in the field, because even though I'm going to talk about water and a pot of boiling water on your stove, it's the basics of what we do every day in the field, okay? It is your air conditioner, okay? Sensible heat, first of all, it's just like it says. It senses. You can sense it. You can feel a difference in heat. Your thermostat senses sensible heat. You have it set for 70. It goes to 71. It senses that and it turns on. Okay. On the other hand, latent is heat that stays the same. It doesn't change temperature, but it's changing state. And my example here is, if you were to put a pot of water on your stove tonight, and I used to do this all the time with my kids or my wife when I learned something, I'd say, hey, check this out. So I often tell our students that go home tonight, put a pot of water on your stove and start boiling it, and put a temperature probe in it. When that water starts to boil at atmospheric pressure, which is 14.7, by the way, it's standard atmospheric pressure, unless you go to Denver and they let you know about it right away. But water will start to boil at 212 degrees. What's cool about latent heat, and I'm a geek, is as long as there's water in that pot, it'll stay 212 degrees. It's amazing. It's physics, but it's kind of cool if you think about it. And that's what we refer to as latent heat, okay? That also is our evaporator. The second that last drop of water leaves that pot of water and it's all vapor, it'll go to 213 degrees. And right beyond that last arrow, that 213 degrees is what's leaving the evaporator. That's also known as 1 degree of superheat, okay? It's 1 degree of sensible heat and 1 degree of superheat. And I know that's not a lot of fun, but it's a nice way to look at our industry. And going back the other way is the condenser. So in the condenser and the evaporator, we're changing state of the refrigerant. In the evaporator, we're going from liquid to vapor. In the condenser, we're going from vapor to liquid, okay? And that's what it's doing. The outside's going to vapor to liquid. The inside's going from liquid to vapor. The evaporator is absorbing the heat. The condenser is rejecting it outside, your air conditioner, okay? So the only thing I want to take away from this is refrigerant piping. The two biggest reasons we have refrigerant piping, the easiest way to remember this is, for me, when I first got started, the two biggest ones that you need to know is the V's. The two V's is in Victor, okay? We need volume and we need velocity, okay? So in other words, if one of your employees or coworkers or customers goes out to hook up a refrigerant line and you just sold them a condenser, if those refrigerant lines aren't right, something's going to go seriously wrong. We need volume. In other words, we need the refrigerant line to be big enough to bring back refrigerant to cool our compressor. Remember, I said most compressors out there are refrigerant cooled. 90% of them are. Okay, so we need it to be large enough for volume to cool the compressor. We need it to be small enough to push the oil back for that velocity. Okay, so those are the two biggest reasons we size refrigerant lines like we do. And if you work for a wholesaler, you know that on your charts, that if you get beyond a certain footage, like beyond 50 feet or 70 feet or something, those sizes might change because now we got a further way to go. This is just a real quick. I don't want to scare you here on it, and I don't know everybody's level and who all does what, but I like showing this in the classroom. But just to start getting people to understand this, I always want people to be able to improve themselves and move up the ladder, and hopefully one day become that service manager or that lead technician or whatever. So this is an enthalpy chart. I'm not going to spend a lot of time on it, but when I showed it the first time, I seen a lot of eyes open from technicians, and sometimes they come in the room like they know it all already, and it really helps break down that barrier because they don't know this. But this is an enthalpy chart, and this is what people that design systems do. Now, I don't want to teach you enthalpy, but I want to show you, if you ever see a diagram like this and you're sitting in a room or you're watching something, I want you to understand how simple this is, okay? And this particular diagram, I put the compressor and the actual symbols in there. This line, this normally wouldn't be here that says compressor, but this line is showing you the compressor. It's defining what the compressor is, okay? The line going across here is the condenser, and the line going down is the metering device, and the line going across is the evaporator. Real quick for you, this is called a saturated curve inside here. Again, I don't want to bore you, but in very simple terms, what that's saying is everything that's inside that thumbnail looking thing is that refrigerant is mixed with liquid and vapor, okay? And that's what's in our condensers and our evaporator. It's saturated refrigerant, okay? It's changing either from liquid or vapor or vice versa. So as long as it's inside there, it is saturated, okay? It gets over here, it's liquid. It gets over here, it's vapor, all right? At the bottom, we have BTUs, and at the side, we have pressures. But that's how people design equipment that you work for, whether it's Trane, Goodman, whatever it is, that's what they're doing. Okay, real quick, I didn't realize I left this in here. What is sensible heat? It's heat you can measure. Any heat that you can measure or sense, it's sensible, okay? What is standard atmospheric pressure? 14.7, okay? That is standard atmospheric pressure. So that's the pressure that's already pushing down on us. When we have our gauges and they're at 0 on our refrigerants, that's already figured into that's 14.7, okay? All right, what type of piping do we use? We use ACR pipe. I didn't mention it. I just mentioned the 2 V's, but it's air conditioning refrigerant pipe. The reason that's important for technicians to know, okay, is it's not like plumber's pipe. Air conditioning pipe is dehydrated. It doesn't have a seam, and it's measured by OD and not ID, okay? The evaporator in the refrigerant state is saturated, as I talked about, and the refrigerant number for water happens to be R718. Now, ACR piping is different than plumbing copper, and name just 2 differences, okay? As I mentioned, refrigerant copper is dehydrated, it's also seamless, and it's measured in OD. The condenser has more than one purpose. Name just 2. Well, it's rejecting heat, and it's condensing the refrigerant. In other words, when it rejects the heat, it's causing it to condense, and it goes from a liquid or a vapor to a liquid, okay? Let's just go over some of the best practices on as refrigerant. And the way this is set up, the way I put this together this morning or last night, is it's going to be actually somewhat walking us through an install. So if you already work with technicians, or you sell to technicians, or you manage technicians, or whatever that looks like, when they're going down to put an air conditioner in, this kind of looks what their day looks like, okay? A little bit, all right? So let's go over the piping procedures. They're brazing the unit in. We need the correct size of the piping, obviously. We talked about the type of tubing already. They got to cut with the proper tools. We're talking about tubing cutters. We're not talking about hacksaws or sawzalls. And I know that sounds funny, but you'd be surprised. And I make joke of that and lie to that because we're all guilty of it, okay? We want to make sure those little copper flakes don't fall down into the copper tubing. Okay, clean and flux as needed. We need to clean the copper. Flux is just a device, a salve, if you will. The only thing I tell the students about flux is, if you're familiar with it, is it's almost looks like Vaseline, if you will. It's like a little. It helps it seal better. It's got some solder already in it, typically, and it brings heat quicker to that area and helps the brazing go a lot smoother. The only thing I warn them about flux is it's acidic. Okay. So we always tell them to use it sparingly and put it on the male fitting, and don't glob it up in the female fitting where you can shove it down the line there, okay? Ensure proper fit and fasten as required. Obviously, follow all codes and regulations, okay? Select the proper heat source and filler material. When we talk about heat source, we've got, you know, the turbo torches, and I know that's a brand name. They're a 1-tank deal. They don't get as hot as like acetylene or oxygen. So you have to be very aware of technicians not staying on the part too long, because that's how new things get burned up or broke real quick, and you think it came bad from the factory when in fact it did not. And I'm talking about like TXVs, service valves. That brass likes to expand because of that heat, like anything else, okay? So when it expands, you might not be able to open that valve anymore, that TXV might not be able to work. Purge with inert gas. This is always a good one because a lot of guys and gals don't even realize this. And inert gas is just a fancy way of saying nitrogen. Okay. Anything that can dry the system out. Okay. We're going to put inert gas in there. Why use inert gas? As I just said, we're dehydrating it out. There's moisture in there. Moisture is bad for refrigerant, especially POE oil refrigerant. It again turns acidic. So we have to be careful about it. We need to dry it out. And this was done at our lab in Sydney, Ohio at the Copeland plant. Okay. On the left-hand side, they did not use nitrogen. So if you work in a contractor's setting right now, this is a good eye opener. It always gets everyone looking right first thing in the morning when their coffee's kicking in, like, you got to be kidding me. So what we see as technicians on the left-hand side is all this black ash over here. That's what's flaking up on the outside of the copper. We don't realize that that's also happening inside the copper, okay? These flakes actually came from inside this copper, by the way, okay? On the right-hand side, we use nitrogen while we're brazing. Now, what does using nitrogen brazing look like? Because a lot of technicians don't do it, and more they're getting used to it, but you really need to get in the practice of it. It's when you braze the line set into your refrigerant lines, you remove the Schrader valves from the condenser or your air conditioner, remove those out of there. Refrigerant hasn't been released yet. And then you just open up a nitrogen tank with the hoses while you're brazing, just a little bit at a time, maybe a pound, pound and a half, if that, okay? So you're just basically not letting that oxidize inside that copper, okay? Because POE oil will take this refrigerant line on the left-hand side and make it look like this. It is as good, if not better, than any flush out there. I mean, RX11 or whatever. Well, the things that the technicians do today that I didn't understand when I first got in the business, and I learned even more at Emerson, is the things we do today, the installers, give them a lot of kudos because they start the ball rolling on how that system's going to run for the rest of its life. Because what a lot of people don't know, and I didn't know, is the things that we do today at Mrs. Wilson's house or Mr. Jones' house or their business actually doesn't show its ugly head until 5 years down the road. So these flakes might not show up for 2, 3, 4, 5 years down the road. And then you show up and Tim, the technician, shows up, and he might even be a new hire. He may have not even done the job, maybe even worked for somebody else. And the homeowner or the builder owner goes, gosh, they just don't make things like they used to, after he tells them the compressor failed or the TXV failed. Well, the fact is they do still make things fairly good, really good. It's just some of our practices have changed. And POE oil really, really changed the industry. And that's about all that's in refrigerant now, okay? When 410A came along, POE oil took over. Okay, just real quick on pressure tests. We're pressure testing the system, and I'm not going to bore you with this all there. We never want them to go above the nameplate on their evaporator to explode it, obviously. I'm not sure if you're familiar. I'm sure most of you are. We're going to use soap bubbles. Literally, it's identical to dish soap that you use. I've used dish soap before. You mix it with water, about a 1-to-3 ratio, and you can put those soap bubbles. It makes it thick over the fittings, which you just brazed. You pressurize that system with nitrogen, and it'll blow bubbles out wherever you might have a leak. So that's just a good visual of what they're doing when they first install the system. At the bottom, you also see some other type of detectors. One's based on sound, and the other one is a sniffer, okay, that can actually smell the refrigerant that goes off and starts beeping, almost like a CO detector, if you will, in your house. Evacuation, we're going to use an evacuation pump. The evacuation pump, the biggest takeaway I want to give you there is we use evacuation to remove non-condensables and moisture. And when I say moisture, what we do is that vacuum pump is vacuuming, bringing that pressure down. It's not 14.7 anymore in those refrigerant lines where water boils at 212 degrees. We're pulling it down. And for example, we like to get things down to 500 microns. Again, that's a fancy way of saying like a -30 on your gauges, okay? And at 500 microns, you're boiling water at -12. I did a little display the other day on my fun facts I put it on LinkedIn too, and it got a lot of hits. And all we were doing when I was teaching in Pennsylvania last week is vacuuming. We were hooked up to a mason jar of water with the vacuum pump, and it showed the water just boiling in there. And it definitely wasn't 212 degrees. You could touch the jar, but anytime you're pulling that down to a different pressure, water's going to boil. at a different temperature. Just like out in Boulder, Colorado, or Denver, Colorado. I go out there quite a bit. I was there 3 times in 2 months, and they were quick to tell me that atmospheric pressure is not, it is not 14.7 here. It's 12.2, I believe is what it was. Okay. The big one here that I want to talk about most importantly is change your vacuum pump oil. If you work with technicians, or you sell to technicians, or you supervise technicians, or whatever that looks like to you, make sure they're changing their vacuum pump oil often, preferably every time. The vacuum pump oil will absorb the moisture that's coming through there. Okay. So when it starts, so don't be, like I jokingly say in the class all the time, don't be like Don. And this has happened to me. I'm just being honest. Don't be like Don and only change your oil when the vacuum pump tips over in your truck. Okay. Or if it's milky white, that's way too far. You can have the best vacuum pump in the world. Okay. And within a month, it won't be pulling down worth a darn because you haven't changed the oil. So I'm not going to share you about the different sizing. More importantly, change the oil. And at last but not least, use a micron gauge. Mercury gauges or compound gauges or refrigerant gauges are not designed to pull down to a proper vac. They're 1/4-inch hoses. It does not work. They're not designed. You can have a 7 CFM pump, vacuum pump, a nice fancy 10 CFM, and through a 1/4-inch hoses, you're only really pulling down like at 3 CFM. So it takes forever, and time is money. Okay. So get you some micron gauges and get you some micron hoses. Okay. Encourage that. This is just a nice snapshot of the gauges. Did you know? Okay. Every one of those hash marks on these refrigerant gauges, these compound gauges or mercury gauges, is 2 inches. The reason I'm sharing that with you, did you know? Because I did not. Between every one of those hash marks is not only 2 inches, but it's also 50,800 microns. Why is that important? Why is that an eye opener to technicians when we teach? Because close doesn't count. In between one of those hash marks, if it's, beer 30 on Friday or whatever that looks like, or lunchtime, or I got to go call my girlfriend or my boyfriend or whatever. Okay. Getting close does not count, because if you're off just a half of a hash mark, you've got 25,400 microns. And what did we say we want? What Emerson recommends? 500 microns or less. Okay. If you are not there, you're not tight and you're not dry. Okay. Use calibrated gauges. Okay. Refrigerant charging. If you're using a blend, which most refrigerants out there are a blend, we ask you to turn the tank upside down. So in other words, where the Schrader valve is on top of the tank, it will be down. Why is that important to know? Because we charge in a liquid. Blends might have 2 or more components. It's like a recipe, if you will. It's like you're making chili or soup or whatever that is, okay? So you're putting all these ingredients in. That's what a blend is. It has 4 or 5 components, different blends, different refrigerants to make one refrigerant. So we want to put that in a liquid state, turning the tank upside down, okay? Because if we put it in vapor state, we have a great possibility of getting a pocket of this vapor and this vapor, and it's not a good mix, okay? So whenever we're using a blend, we put it in the liquid side. The unit's not running now. We charge the unit. We haven't released the refrigerant in your condenser or your air conditioning at your house. Brand new system for Mrs. Jones. Okay. The valves are still closed. Okay. Typically, if you don't know this, and I say typically because nothing's sketched in stone, your air conditioner at your house, when you first get it, it's been like this for years, comes with about 15 foot of charge in it. So if this line set is longer than 15 foot, a technician should and will charge the system with a little bit more. It might only need a pound or so, but we're putting that in a liquid state, and it's coming in the liquid line side and coming up to here, and we're weighing that in, okay, with the tank upside down like this. Best practices, again, initial charge, liquid, high side, topping off. If it is a single component like R22, if you remember that, okay, that is a single component. You can top off that with vapor, okay? Again, remove blends from the cylinder as a liquid. Use charging charts. When we're talking about charging charts, we're talking about PT charts. But if you don't know this, your gauges are PT charts. Those numbers in there, that's what the temperature is inside the evaporator or the condenser, okay? It's just matching the pressure with the temperature, okay? My most important thing that I preach is verify airflow across the evaporator and the condenser. If airflow is not right, if you go out to your air conditioner tomorrow or next summer or whatever, and you see a bunch of grass clippings or tall grass or ornamental grass growing up around your air conditioner, that is terribly bad on your air conditioner, okay? It has to breathe. Remember, it's pulling it in from the side and rejecting that heat at the top. The further away you can keep that air, anything around there, including your house, the better that thing will breathe, okay? So if that airflow is not right, for example, if there's grass clippings, if someone's mowing your lawn or someone, you know, in the family's mowing the lawn and they're aiming that towards the air conditioner, if they mat that all up, when someone goes to put their gauges on, like this slide shows, the pressures are going to be much higher. When you suffocate that, the pressure goes up. Remember, we said temperature, pressure have a relationship. It gets hotter, the temperature and pressure go up, okay? And if you had your gauges hooked up and out in your yard, a technician, okay, and you turn the sprinkler on to prove that fact, once you start cooling that air around that condenser and you're gauged up, your gauges will actually drop, okay? Everything starts with temperature, all right? The only reason we gauge up outside to read the temperature from inside in the evaporator is we use the law of physics, but because there's no way we can take a temperature probe and put it in the center of the evaporator or above your furnace or your air handler, okay? Verify superheat and subcooling. Again, my objective here today wasn't to make you all be technicians. Maybe you were already in your past lives. I don't know. My biggest thing is my hope, anyways, my goal, and I hope I accomplish is just to get a better understanding of what, if you don't already know, what do they mean by superheat? What do they mean by subcooling? First of all, the way I like to remember this is when we talk about superheat, we're talking about a vapor. Refrigerant is in a vapor, okay? When we're talking about subcooling, we're talking about liquid. Now, the best way to remember vapor is, I'll touch on that here in a little bit, is the best way to remember this gauge is, I want to show you some examples here. Here's 3 different refrigerants in your gauges, okay? A typical technician's gauges. We've got R12, R22, pardon me, R12, and then R502. Now, whatever pressure this is on the outside, you come into this ring in the center here, these lines, and match them up with the refrigerant, and that's what the temperature is. For example, if we're using R22 at 38, 37 pounds of pressure, we're at about 40 degrees. You see how that works? And this is a PT chart. What does that mean to you? So if you don't know this, the blue gauge, when you use these old compound type gauges, if you're not already went to digital, this will tell you the suction side. And and the suction side is what's inside the house. That's the evaporator, okay? So these are the temperatures that's in the evaporator. So it's 40 degrees at R22. So as long as that air coming through your house is warmer than 40 degrees, obviously it would be, it's absorbing heat, okay? On the other hand, on the red gauge over here, this is what the condenser or your air conditioning outside is saying. Now, again, if we're using R22, the pressures he's seen is 205 degrees or somewhere thereabouts. We're looking at about 138 pounds or 138 degrees, pardon me, okay? 205 pounds, 138 degrees. I know that's something you'll probably never need to use, but this is in fact a PT chart. This is what a good technician is using every day. This is what a good technician, if they went to a vocational school or a college of any sort, or one of our classes or any of our competitors' classes, these are the basic fundamentals they have to understand. They have to know how to take superheat, and they have to know how to do subcooling. Vapor is superheat, subcooling is liquid. Vapor or superheat, by the way, is any vapor above its boiling point. So for the example of water at that 212, any heat added to a vapor above its boiling point, in water's case, that would be 213. That's 1 degree of superheat. Any heat below its boiling point, 211 in water, is subcooling. So if you're drinking a bottle of water right now, that's subcooled liquid, because at atmospheric pressure, water boils at 212. So anything below 212 is considered subcooled liquid, all right? This just shows you the PT chart. This is one of our apps here, okay? So what a person would do with this app, and our competitors have these apps. I'm not trying to sell you on these apps. In fact, the hidden agenda behind our apps, quite honestly, people, wonder what's going on. Are you going to charge for them down the road? Are you getting us hooked on them and then you're going to charge for them? No, the answer is no. Do they cost a lot of money? Absolutely they do. Okay. A lot of IT, a lot of software, a lot of things constantly being updated. We've got one app called Copeland Mobile. It is the bomb. If you've never heard of it, please get a hold of me or Colleen or Pam that's on the line. It'll blow your mind. Once the technician finds out about Copeland Mobile, their whole world changes. But real quick on this. So instead of using, when we read our gauges that we just showed you, we would put our numbers right here, PSIG, that's our pressure, okay? So we put this 100 pounds of pressure there. When we hit the button as it drops down, done or finished, it would give us the saturation temperature. And since we're dealing with vapor, this is what's inside the evaporator or inside the house or the building, your business, okay? It would pop up here. Now, when you take superheat, you take the temperature that's inside the evaporator and subtract it what's leaving the evaporator. That's the cool thing about subcooling an evaporator. If a person only focused on this on day one, it's quite simple. Superheat is nothing more than taking the temperature inside the evaporator and subtracting it from leaving the evaporator. So if it's 31 degrees in the evaporator and it's leaving at 41 degrees, you have 10 degrees superheat. It's just that simple. And a lot of people go throughout 10 years or their lifetime. I've had people as old as 50 some years old come up to me at first break and said, you were the first person that ever showed me how to do superheat. And I'm not kidding you, it touches you. But subcooling, on the other hand, is the same thing, but it's the air conditioner outside. You're taking the temperature of what's inside the condenser, okay, on your gauges, and you're subtracting it leaving your air conditioner or the condenser, okay? What's inside. We can't physically take a temperature probe and put it inside that coil. So again, we use physics. By taking the pressure, we know the temperature, all right? That's why we gauge up, okay? All right, we have 3 different refrigerants conditions in a system. We have saturated, hopefully you remember what that is. It's vapor and liquid mixed, okay? It's both, all right? Where would we find saturated refrigerant? We'd find them in our coils, okay? Evaporator inside and the condenser outside at the air conditioner, okay? Superheated refrigerant, that's any vapor above its boiling point, heat added to it, okay? So I always use water as the example because it's a good analogy, and it's 213 degrees. So that's 1 degree of sensible heat. It's also 1 degree of superheat. Subcooled is always heat removed from a liquid below its boiling point. In the case of water, or R718, it'd be 211 degrees, okay? Now, which one of those refrigerants do you think transfers heat better? Is it liquid or vapor? And typically at this time in the morning, I get people kind of hesitant because no one's talking yet. And then you finally, what is it, vapor or liquid? And you might get 1 or 2 or 3. And then his hands go up, someone, more of them and more of them. Okay, let's do it this way. How many people think it's vapor? And you'll get, let's say it's a class of 24. 10 of them saying it's vapor, and 14 of them saying it's liquid. And then I give them a visual. The way I was taught, the best analogy I've ever heard, I tell them, think about this. You have to sleep outside for 24 hours. It's 60-degree air temperature outside. You can wear whatever you want to, shirt, short sleeves, long sleeves, pants, shorts, whatever. Will you survive in 60-degree air? And the answer is yes. Now I want you to visualize, will you survive 24 hours standing in your swimming pool or a lake or an ocean in 60-degree water up to your neck? You don't even have to swim, okay? The answer is no. And it would depend on your body mass, because that air, that liquid just absorbs that heat right out of your body, okay? So heat or liquid is a much better transfer of heat than vapor is, okay? That's why the majority of our saturation going into the coil is liquid at the beginning, okay? It's not until the very end that it turns completely vapor. But liquid is a much better mover. That's why we have boilers. If you're up north, you might heat your house with a boiler. It's transferring that heat, okay? All right, this is just an example of what that might look like in saturated refrigerant. Okay, give you some examples here. I put a fancy gauge on here that's reading 290 PSI. Okay, they're saying we're using the refrigerant 404A. Don't hang your head on the fancy refrigerants or whatever, and you might even sell this. But really what I want to show you is My temperature probe is within 6 inches. If you want to write that down, that'll help a technician. We like you to take your temperature and pressure readings within 6 inches whenever possible. So it's telling me my new fancy little clamp on here is telling me that that refrigerant line's 115 degrees. The pressure shows me it's 290. We're using 404. So we would go to what we call our PT charts, which is your gauges, kind of, sort of. Okay, your PT charts, which is saturated refrigerant. And what we'd find are our PT charts at this pressure for 404A. We would take our hands, our fingers, and identify the refrigerant 404A, go down to the pressure, bring our fingers together, and we should find that it's 115 degrees. The moral of this story, everything in that refrigerant line is in fact saturated, okay? Where would we find saturated refrigerant to bring it home? We would find it in the evaporator and the condenser, okay? On the evaporator, again, we're going from a liquid to a vapor, all right? We're absorbing heat there inside the house or the building. Out here, we're going from a vapor to a liquid. As we reject the heat, we're condensing that refrigerant from a vapor back to a liquid, okay? Let's talk about superheat. Superheat, again, first and foremost, is a vapor. If they're looking for superheat anywhere else but the suction line, they're doing it wrong. And believe me, it happens all the time. When I was a service manager for 9.5 years in Fort Wayne, I trained a lot of people. I was blessed to work with a lot of good technicians, learned a lot from them, and hopefully I taught them some things, okay? Again, superheat, we're taking the pressure, 74 pounds for 404A, and we're reading the temperature line. We go to our PT charts. It's going to tell our PT chart's going to say it should be 33 degrees inside the evaporator. We're taking this temperature outside the evaporator at 43 degrees. The moral of this story is what's inside the evaporator, what's leaving the evaporator is 10 degrees. That's 10 degrees of superheat. That's how simple it is, okay? And you'd be surprised. I know when I was first taught, God bless them, I learned a lot, but the older guys that taught me, the age that I am now, okay, when they were teaching me, I'd be looking over their shoulder like 26, 27 years ago, and I'd say, what should the gauges read? And the guy, God bless all of them, they would say, well, on temperature like today, we're looking at about 70 pounds. But really, to be honest with you, they weren't really, technically doing it correctly. They were just kind of ballparking it, if you will, somewhere about 70 pounds. But this is the right way to do it. You know what your gauges are telling you. Whatever that temperature is, just subtract whatever it's leaving, okay, the evaporator or the condenser. So that's superheat. Now, where would we take superheat at? By the way, this is a TXV, if you didn't know that. This is our metering device. I'm sure you do. This is how this works, okay? A TXV is metering the refrigerant as it's coming in. Remember, it's also a pressure drop. Without it, we wouldn't be able to build up pressure. It's metering it. Think of a little orifice, okay? And it's allowing so much refrigerant in. And as it's coming through there, think of a spray bottle, a Windex bottle, or a water bottle, if you will. That mist, that atomized, that's what it's doing. It's coming from a liquid on this side, changing from a liquid to a vapor. But it's mostly liquid when it leaves, and then it starts to absorb heat, and it turns to a vapor. The real thing I want to point out to you is metering devices like this, the reason they work so much better than like a piston is because there's a bulb over here reading the temperature of the refrigerant line leaving the evaporator, okay? This is the TXV bulb. What's inside that TXV bulb? It could be any component. Sometimes it's the same refrigerant that's actually in the system, okay? What is it doing? Well, when this refrigerant line gets hot, there is a pressure temperature relationship, okay? The hotter it gets, the higher the pressure goes up. And how it works is it expands that gas in that bulb. This line here has a little orifice or a little hole in it, and it pushes back as it raises the temperature, it raises the pressure, and it pushes down on a diaphragm here. So if it's too hot leaving, it actually opens this TXV up more and allows more liquid refrigerant, okay, to go through there, and then it gets cool here and it adjusts all day like that, okay, up and down. But think of it as a little diaphragm, okay? If it's too warm, it gives it more refrigerant. If it's too cold, it shuts it down, all right? And that's the way it works. Now, where do we take superheat? Well, if you're taking superheat for the system or the designer or for the evaporator, you would take it here, beyond the bulb, by the way. You would take it right here, all right? You take the superheat reading here, all right? Now, when you take this reading, again, you read your gauges, whatever it says, and you're subtracting the heat from inside here to here, okay, whatever the difference is. All right. The reason you're taking here is you want to make sure that this TXV is working properly. It's matching the load, if you will. It's doing what it's supposed to do. Now, when you take superheat here, if you're talking to a compressor manufacturer like Emerson or our competitors, we're taking superheat here because we want to confirm that we have vapor going into our vapor pump. Remember, as long as we have superheat, we know it's vapor. If it starts to turn liquid, we won't have a superheat reading here. All right. We're still taking a temperature reading here and subtracting it from whatever our gauges say, that blue gauge or that vapor or that suction side. Okay. If it's digital, it'll be the suction side. All right. Now on the back side of this is also superheated vapor, but we're not taking a reading here. But if you'd like a little fun fact that a lot of people don't know, in fact, almost every student that I teach or I help teach doesn't know, we never want this temperature 6 inches outside a compressor to be higher than 225 degrees. Now, before I go any further, that'll hold true for any semi-hermetic compressor and about 90% of the scrolls out there, okay? This picture is a scroll compressor. So it's good, and that reading's been around for a long years. What they found is we lose somewhere between 50 to 75 degrees of temperature at the hottest point of almost any compressor, from the hottest point to 6 inches down the discharge line. So keeping with the theme the theory that we might be worst scenario, we lose 75 degrees. If you add 75 to 225, that's 300, obviously. 300 degrees inside that compressor. We have no way of checking the temperature of the compressor unless we do it like this. You take that temperature reading at 225, you assume that you lost 75, you add it together, that's 300 degrees. The significance is there, if you don't already know, is oil starts to break down at 300 degrees, okay? And that's when everything goes bad. All right, 225, stay alive, 6 inches down that discharge line. If you share that with a technician, they'll love you forever. If you're working with technicians or you supervise technicians or whatever that looks like, share it with them. Add it to your tool belt, okay? Put it on your invoice. It'll tell you everything. If it's over 225, you need to start backing up on this line and finding out why. Maybe it's too hot back here leaving the evaporator. Maybe this TXV isn't working right. Maybe the insulation's off this suction line and it's in an attic and it's absorbing heat. Remember, hot likes to go to cold. If that's an attic at 200 degrees, it's absorbing that heat and picking it up and making it 235 or 245 out there. So get in the practice of using that. Okay, I'm going to bring it on home now. We're going to do subcooling. Same thing as before. We're taking whatever our gauge reading is, 280 PSIG, okay, whether you're using digital or the compound gauges. We're taking our temperature reading, preferably within 6 inches. It's 170 degrees, it says. If we were to go to our PT chart or whatever our gauges would say, it should tell us it's 113 degrees, okay? Subtracted from 107 is 6 degrees. We have 6 degrees of subcooling. The way I like to teach this is subcooling means the condenser. That's where we're changing vapor to liquid. Subcooling is a liquid. The same thing as superheats over here in the evaporator. So if we know that, if we know the air conditioners where subcooling happens, we should know that whatever our gauges say on our high side or the red gauge or our subcooling, it's telling us the temperature about midpoint in that condenser. How do we do subcooling? We literally take the temperature leaving the condenser, subtracting what's inside the condenser from our gauges, and that's our subcooling. It's quite that simple. If they're checking subcooling anywhere else but this blue line, they're doing it wrong, okay? And you'd be surprised. I've talked to technicians before as a service manager, and I finally say, where are you taking that temperature reading at? And I'm on the discharge line. Terminology sometimes can be confusing, whoever's training you. You have to be in the liquid line to be checking subcooling, okay? I like to take reading here on subcooling because if on both ends, but I especially like to take it here also because we need to have, it's as important to have liquid going into this TXV or this metering device as important it is to have vapor going into our vapor pump, okay? Again, these two lines, remember home base and second base, our compressor and our TXV, okay? That's our home plate and our second base, okay? We have everything high side over there, low side over there, that imaginary line. So this is the final slide. I hope I didn't bore you too much. If you're taking notes, remember this. Not only is this a suction line, it is low pressure superheated vapor. The suction line equals low pressure, superheated vapor. The discharge line equals high pressure, superheated vapor. Okay. The liquid line equals subcooled or high pressure, subcooled liquid. Pardon me. Liquid line equals high pressure, subcooled liquid. And of course, the green, what does it identify? That's saturated refrigerant. Saturated is defined again as liquid and vapor mixed. All right. I hope I didn't put you to sleep. Hopefully we still have somebody on the line.
It was great.
Yeah, I'm pretty sure people are still here. You've been getting good feedback in the chat.
Good.
Everybody has enjoyed the presentation, and especially the baseball analogy was earlier, and everybody wants a copy of the slides.
Cool. Great.
Soph's had a lot of great detailed information in a short amount of time. Thank you. And lots of good information. I want to copy the slides. Great presentation. Lots of things going on in the chat for you, Don. So sometimes not having questions might be a good thing. Is there anybody that has any questions, any follow-up, any insights, something you learned, feedback?
Very good presentation, Don. I really appreciated it.
You bet. You bet. My pleasure. I hope you got something out of it. I tried to do my best. Again, I know we're not going to walk out and be technicians out there today or tomorrow, but if you're working with people, it kind of helps it bring you understand things a little better where it is. Like try, and this is the way I teach all the time. I try to simplify things as best I can.
Yeah, it's not in what I do for work. We're on the temperature control side, thermostats and controllers for different pieces of equipment, but it was very interesting.
Good. I appreciate that. Thank you.
I have a question.
Sure.
On the apps, because it looks like I went on, you've got a ton of apps to choose from. Which would be like the top one or two for the field technicians that I could tell them that they should look into first?
So if they would download Copeland Mobile,
okay, got that one.
It is free. If they should ask you to register, tell them not to panic. They're not going to send you a bunch of email. I promise you, we do this for every class. I have them download these apps before we get started because a lot of those exercises, some of them you saw, some of them you didn't see. I actually work with them and they actually do those drills in the classroom just to get them comfortable with it. Okay, Copeland Mobile. All you need is first 4 characters of your condenser or your compressor, and you can look up service parts if you're looking for something. It is so cool. I mean, it's got a GPS on it. It'll even tell you the closest wholesaler where to buy it from. I mean, it'll blow your mind. It'll just blow your mind. I know I sound geeky, but it will. Technicians will love it. So, and it's free. Copeland Mobile. And the other one is, I like the PT Pro that I showed you. Some of our competitors have, as good as, if not equal, obviously. But the other one I like is if you're in the air conditioner world, if you're only in air conditioning and not in refrigeration, what does that mean? I'm talking about residential or light commercial. There's one that's called an E-Saver. It's green in color. Okay, when you pull it up, it has a big letter E on it, and it's called E-Saver. It's short for Energy Saver, and this is a really, really cool app. If you want to separate yourself from your competitors, you literally don't even have to take a notebook out. You just literally, if you put the city in that you're working or the state that you're working, like Ohio, and then you say, and then it's going to ask you to pick your city. 9.9 times out of 10, your city's on there. They're larger cities, but just put like Columbus, Ohio, or whatever large city you're closest to that comes up. Okay. When you do that in real time, it'll actually calculate the run hours for air conditioning and heating. Okay. Why is that cool? Because then you put in whatever efficiency they have on their air conditioner or their furnace, and then you put in what you're offering them, quoting them. It doesn't have anything to do with monies. It's not branded in any way, shape, or form. But in real time, what Copeland does or Emerson does is they keep that calibrated. Every midnight, it calibrates itself and keeps calculated. It can tell you what you're paying for kilowatts in that area. It can tell you what you're paying for natural gas in that area. And what's really cool about it is at the end of when you fill all the information out, you have a way to email it to your customer that has a nice PDF that prints out in color if you want it to be, that tells you, my first 5 years, if I buy this system, the payback will be, 5 years or 3 years or 2 years, but it's a really good visual for a customer to look down. You can use it for a family member. I mean, it's free. You know what I mean? If you're thinking about buying a system, you can actually put in, okay, I've got a 10 SEER air conditioner. I'm thinking about going to a 16 SEER air conditioner. It will show you the peaks and valleys, what you're going to gain and lose in the winter and the air conditioning based on months. If you're in
Wow.
Atlanta, you might have 1,200 cooling hours. If you're in Chicago, you might only have 400 cooling hours. So it's really cool that it turns into like a GPS and calculates for each area you're in. I really like that one. And then last but not least is what we call the AE app. And it is Application Engineers Bulletin. Now that can sound a little overwhelming that it's engineering, but I'm here to tell you, when I first came to Emerson, I had to learn a lot like all the trainers do. I literally just read application engineer bulletins on the Copeland products or the Emerson products, and it really expedited my knowledge in the first year. It's a very simple read, and I'm the kind of guy that sometimes I have to read things twice, but it's very, very easy. It's not a lot of large vocabulary words. It keeps it very simple. It can be as simple as, what's an accumulator? You know, how often should I change my filter, to the most extravagant thing and all you have to do is, it's like a Google search. You just put the word like torque in the search bar and it'll literally pull up all the torque values of everything that Emerson makes, how tight that bolt's supposed to be. That's just one example. Really, really cool. Really good stuff. I mean, trust me, the technicians will love it. I know
Awesome.
I sound weird, but they will.
All right, we're gonna
Thank you
try
very much.
something a bit different, a bit new. Don, if you don't mind, just because of some of the interest and some of the apps you laid out, and including your presentation, if it's something that you're willing to share, and that Emerson's willing to share, if you could do a quick, if you could for me, I know you're with your family, but even if it's next week, if you could write up a quick email with like just a synopsis and some of those links to those apps, and your slides. That's something I can send to everybody afterwards. It's just, we're trying to figure out a way to facilitate it. Every time we have these Zoom meetings, we got more and more people and everybody's like, I want the slideshow. And it's like,
Sure.
not that easy to send it all out to everybody all the time.
Sure.
Especially when you have to get a list. So if you could do a synopsis, just a wrap up of the call, what apps you were talking about, that's the big thing that everybody wants to see. And the baseball diamond apparently was everybody's favorite. So